Okay, welcome all. In this video, we'll be talking about how you measure process performance, the important metrics, and we'll talk a little bit about something called Little's Law, right? So, as I was saying at the end of the last video, measuring process performance is an important thing. So, whenever you have a process, you need to know how well the process is working. So, some of the important metrics are flow time, cycle time, and throughput rate, which are basically the same thing. One is a reciprocal of the other. Then you have efficiency, productivity, and utilization. So these are all important metrics. We saw productivity in class last time, and efficiency and utilization is something that we'll talk about more later on, right? So in measuring process performance, like we talked about with productivity, benchmarking is always important. Comparing metrics within the company and also with other companies and um, general expectations of a sector, right? So we talked about productivity and efficiency similarly. So efficiency is the ratio of the actual outputs of a process relative to some standard. So how well are you doing? So efficiencies are something that people talk about all the time. One example of efficiency that I can give you is when people say install solar panels on top of their say houses so that they can use solar power for electricity rather than drawing from the grid. The individual units that are there in the solar panels, the efficiency for them is somewhere around 10 to 12%. That seems like a very low number, right? But in reality, that number has increased a lot. So back in the day, very early days of solar power, the efficiency ratios were in single digits. Now they've gone to lower two digits, and it's very hard to get them above that number because of many reasons. I mean, the angle at which you have to put the thing and so on. So that's a lot of things that go into efficiency. But calculating efficiency is extremely important, right? So flow time, like I said, is an important metric. So is setup. So knowing the setup time and run time and operation time, we can calculate flow time, and of course, process velocity or the throughput ratio. We can calculate the throughput ratio. Like I said, throughput rate is essentially the inverse of the cycle time, right? So these are all metrics that we should calculate. Now, Little's law is an important idea in process analysis. Now, it tells you the long-term relationship between inventory throughput and flow time. Now, one thing to realize that Little's law applies one A in the long term and B as an average. So sometimes, so when you run the same process over and over again, you unless it's a robotic assembly line, not every part that's manufactured doesn't happen in the exact same way. There are always slight differences. Sometimes it might take 10 seconds, sometimes it might take 11 seconds, sometimes it might take 15 seconds because some person doing something missed something and so on. But Little's law is something that calculates things over a large period of time and in average. So when you say that inventory is throughput rate times flow time, you're saying the average inventory that you hold is equal to the throughput rate times the average flow time, right? So that's the idea. So let's look at a simple example of Little's law. But before I do that, quickly, inventory turns and days of supply. These are very simple ideas. The names themselves tell you what it means. But average value of inventory. So sometimes you look at inventory as the number of units that you have on hand, but sometimes you also look at it as dollar value that you have on hand. So if you ever look at balance sheets, inventories are always put down in the assets column, right? So it's important to know how much inventory you have. So you can have finished goods inventory, or you can have work in process inventory, or you can have raw materials inventory. So these are the three types of inventory that you can hold, and the value of each of these is very different, right? It's the same raw material that become work in process, that become finished goods, but once you have made finished goods, their values tend to be much higher than say what you have in work in process, which in turn tends to be higher than what you had as raw materials. Yeah. Okay, so let's get back to this example that I was talking about. So let's say that we look at car batteries. The average cost of car battery is $45, and it takes 12 hours to make a car. Now, let's say that there is an assembly line that can assemble 200 cars per 8-hour shift, and we currently only have one shift. And this particular factory holds an average of 8,000 batteries in raw material inventory, right? So, how much total inventory does it hold? What is the value of the inventory? Those are the things that we want to calculate. So, apart from the raw material inventory, you also have work in process inventory. We are not going to look at uh, for the end product inventory, right? Those are the three types of inventories that we have. We're not going to look at finished goods inventory because once the car batteries become part of a car, you're not looking at individual battery inventory anymore, right? You're looking at car inventory, the number of cars that you have. So when you're looking at car battery inventory, you have 8,000 batteries in raw material, but you also have some batteries on the floor as work in process. Batteries that you might not have completely installed in cars or are installed in cars that have not been manufactured fully. So, how much inventory is that? So, on an average, so when we calculate work in process inventory, we can use Little's law, which is throughput times the flow time. Now, based on the data that we have, we know that flow time is 12 hours. It takes 12 hours to make a car. That's how long you take to make a single one of these items. So that's how long it's going to take for it to go from raw material to finished goods. So that's the flow time. And then the other is throughput. Throughput is how many batteries can you make in an hour, given that we are looking at times in an hour, times as hours. So if you look at the data that you have, you can make 200 cars in an 8-hour shift. So in 1 hour, you'll be able to make 200 divided by 8, which is 25. So you'll be able to make 25 cars in 1 hour, which means you will use up 25 batteries in 1 hour. So the amount of work in process inventory that is on the floor is 300 batteries because they have not gone through the whole of their assembly just yet. They are almost done, but they're not completely done. So there are 300 batteries on the floor and 8,000 batteries that are raw material. So in total, you have 8,300 batteries in inventory. So if like we said, if the cost is $45, the total value of inventory is $373,500. And finally, the flow time for this for the battery is 8,000 divided by 200, which is 40 days. So for the 8,000 batteries that you have on hand, they will last you 40 days, right? Because each day you're using 200, you're making 200 cars, which means using 200 batteries, which means the 8,000 inventory that you have will last for 40 days. So these are two simple applications of Little's law, right? Very simple ideas, not complicated. So remember, Little's law is throughput rate times flow time is equal to inventory. So first we use the straightforward application of Little's law, but here in the second case we sort of shifted it around, right? So instead of saying inventory is throughput time flow time, you want to calculate the flow time for the amount of inventory we have on hand. So we'll just say inventory divided by throughput is equal to flow time, and we know what inventory is, we know what throughput is, so we know that flow time will be 40 days for the 8,000 batteries that we have on hand, right? Now, job design decisions and um, uh, are important to look at. So the two important things to think about when doing these job design decisions. There are two things that you could do. So you could have people who do a single thing and single thing only, right? So that is specialization of labor. So they can either specialize or they don't specialize. So if they specialize, it means that they'll be doing the same thing over and over again. So that is good because that is good for the company because it will be high speed. Low cost production is possible because people doing a certain amount of certain kind of work will keep doing the same thing over and over again. But it has adverse effects on workers because you have repetitive stress injuries. People sometimes get bored in their jobs. They might not take ownership of the product that they make because they're only making a very small part of it. But you could do other. But if you do many different parts of a job. So instead of just doing one part of an assembly line, if you're given the opportunity, if you give the workers the opportunity to do multiple parts of an assembly line, they might take better ownership of the product. Also, there are other things that you could do. I mean, you could uh, give workers incentives on the products that they make and pay them better and things like that. A lot of things that you can do for job enrichment here. Now, I'm not going to talk about work measurement much. I'm going to end the video here. You can read about work measurement in the textbook. It's really not that important. What I want to talk about next is how you actually do process analysis. How do you calculate these metrics that we keep talking about with process analysis, right? So the next one, we will look at a bread making example. We'll look at a restaurant example and solve some of these some basic problems. And we'll talk about process analysis, process capacity, and all of those things, right? Okay, that's in the next video. Take care.